Alright guys, welcome to another fun-filled chemistry video. Today we're going to be talking about periodic trends. We're going to be looking a lot at the periodic table. I don't know if you guys look at comics, but you can imagine being a hairstylist for comic book characters. That would not be fun. Check out the hairstyles. What a nightmare. I can't believe the hairstyles I have to deal with. Okay. So, you guys, I'm hoping you guys could fill this in, what you think. Metals. Oh, you know what? Before that, probably want to show something here. Let's before we do that, let me go over here. I want you guys to hopefully you guys have a periodic table that you have printed out, because then it would be really easy if you can really divide up all pure elements into one of three categories. We have metals, nonmetals, and metalloids. So metals have certain properties, nonmetals have certain properties, and the metalloids have properties that are kind of like both. So you guys will notice, look, the vast majority of all the elements that exist are metals. And so if you want to, you should remember, you guys, where are the metals located? You say from the center to the left, those are all metals. Remember, the one exception that's on the left that's not a metal is, I don't know if you guys remember, the element number one, atomic number one, is hydrogen. And you see that's a blue, indicating that's a nonmetal. So with the exception of hydrogen, where the nonmetal is located on the right side of the periodic table. Okay, so we're going to be looking at what might be responsible for the certain kinds of properties that metals and nonmetals exhibit. And then there's a few metalloids. They're also called semi-metals. That would be like boron and silicon, germanium, arsenic. But just remember, metals on the left, nonmetals on the right. Okay, so the question then I had is, so remember, metals are on the left side of the periodic table. It says metals have a tendency to what? What do you guys think? Guys, with electrons, you're either going to, well, we'll just say it, they're going to have a tendency, well, let's look at this here. I think you guys might be able to make a prediction. So this, we can use what's called the Bohr model of an atom. So if you look on a periodic table, here, you know what, I'm going to go back to that periodic table. So you remember magnesium, if it has atomic number 12, would have 12 electrons. So where are those electrons located? Remember, we can use our periodic table to help determine that. So here's our magnesium. Okay, so here's our magnesium. It's got 12. So now you guys remember, the periods can kind of correspond to shells or energy levels. Okay, so we have 2 electrons on the first shell. Okay, and then we have 8 electrons. You guys, right? We have 2 in the s orbital, the 2s orbital, and then 6 in the 2p orbital. So I just show 8. Okay, and then magnesium has 2 electrons on the third level. You guys remember what those are called? Those are the valence electrons. So then, you guys, what do you guys think? Now, that being said, right, magnesium is a metal. What do you think magnesium has a tendency to do? Remember what we said, atoms tend to gain or lose electrons in order to fill their outer shell. What do you guys think is going to happen? And hopefully you guys guessed correctly. It's going to tend to lose electrons. It's going to tend to lose those valence electrons. Okay, when you think about it, so it'll tend to lose electrons and thus become, now think about it guys, magnesium originally had 12 protons and 12 electrons, right? And so those would balance out and it'd be a neutral charge. Well then if it loses, and what would we expect guys? Lose 2 electrons. Now it has 12 protons, still the 12 protons in the nucleus, but now it only has 10 electrons, and we see it acquires a positive charge. We'd say it would become positive, a positive ion. You guys remember what the word for a positive ion is? Think cute little kitty cats. Cation gives us positive feelings. Those little kitty cats give us positive feelings. Okay, now with a nonmetal, nonmetals tend to, okay, you guys are going to do sulfur. Here, I'll just show you guys here so you guys can do it with me. So sulfur would be an example of a nonmetal. You guys remember where the nonmetals are located? Nonmetals are located on the right side. Here's sulfur right here. Well, you guys look, it's got 2 electrons in the first shell. It's got 8 electrons, I just count over. It's got 8 in the second shell. And then you guys look here, it's got 2 in the 3s. Remember, this is the third energy level, the s orbitals. And then it's got 4 in the p for a total of 6. Okay? And just so remember on this one, we expected magnesium to lose these 2 electrons. And you guys see, by losing the 2 electrons, now it only has 2 shells of electrons. Its outer shell is full. It's and you guys see, when it does that, it then has an electron configuration like, check it out. It has an electron configuration. Notice it only has 10 electrons. It's going to have an electron configuration like neon, right? When magnesium loses these 2 electrons, now it has a configuration like neon. What do you guys think is going to happen to sulfur? What would you guys predict sulfur would do? You might predict sulfur to gain 2 electrons. See, because by gaining 2 electrons, doesn't it now have 8 in its outer shell? And you guys see the third energy level, or the third shell, can hold a maximum of 8 electrons. And so upon doing so, it acquires a configuration just like argon. See, because it had 16 protons and 16 electrons initially, and therefore neutral charge. But then if it gains 2 electrons, it still has 16 protons, but now it has 18 electrons, and therefore it has a negative 2 charge. And once again, you guys, what is significant about the noble gases? Remember, the noble gases, those are the elements whose outer shell is already full. So it's not surprising sulfur would gain 2 electrons to acquire a configuration like argon. Argon's happy, fat, content, stable. You can notice we call them the noble gases. Think about noble. They're like royalty. They're like sitting there feasting. They're having a good time. They're content. And you know what? All the other elements, so these are like the nobility. All these other elements are wannabes. They all want to be like the noble gases. So what do? They tend to interact with other atoms to gain or lose electrons in order to achieve a noble gas configuration such that the outer shell is full. So nonmetals tend to blank electrons. What do you think? When you agree, they tend to gain electrons and thus become, come on, negative. And you guys remember what we call negative ions? Those are called not cations, but anions. Onions don't like onions. Okay, we're going to do a little physics here, guys. And here we have magnets. And you guys know, if I do the opposite poles, they can be an attraction. You remember magnets have a north pole and a south pole. And just like electric charges, opposites attract, opposites poles attract. You guys can see that? Okay. So, the question I have is, let's say we have 2 magnets. What's going to affect the force of attraction between, oh, and you know what? Let's just liken it to protons and electrons. I could like that. I could just act as if this is like a proton and this is an electron, and what do we know? They have an attraction for each other, right? Opposite charges attract. So what might affect the force of attraction between two particles, like these 2 magnets? What do you guys think? Wouldn't you guys agree? Doesn't the distance, because I think about it, guys, I got a net here, I don't feel anything. I don't feel anything. Wait a minute. Wait, I'm starting to feel something. Ooh, yeah, I'm feeling it. I'm feeling it. I done felt it. You guys get what I'm saying? So there's a difference. The further the distance, the less the force of attraction. The closer the distance, the greater the force of attraction. And then there's one other factor, though, that's going to affect the force of attraction between 2 oppositely charged particles. It's not just the distance between the particles, but get this, guys, also the amount of charge. Think about this, Big Daddy. You can see a bigger magnet, greater magnetic field, greater force of attraction. It's the same thing with protons and electrons. The greater the charge, the greater the force of attraction. What we just described here is represented mathematically with Coulomb's law. Now, you guys don't worry, I'm not going to have you guys do physics. I'm not even going to have you guys work with this equation, but it does make sense. F is for the force of attraction, right? So the force of attraction, what do you guys think Q1 and Q2 are? That would be the size of our charges, the size of the positive charge, the size of the negative charge. You guys see that's in the numerator. And wouldn't you guys agree that if these numbers become bigger, remember when I used the larger magnet, what was the effect? A stronger force of attraction. Wouldn't you guys agree? If these are in the numerator, if I make these numbers bigger, isn't that going to, overall, isn't this value going to be larger? So you can see mathematically it works. And then, so that's the amount of charge. And then the R That is the distance between. You guys will remember, right? And you guys notice where the R factor is, the distance, it's in the denominator. What happens when, if we increase the distance, if we increase the number in the denominator, what happens to the overall value? Mathematically, you should know, if you divide by a larger number, overall it's going to be a smaller value. And didn't we say that? The larger the distance, the less the force of attraction. But let's say the distance becomes smaller, so that if this number on the denominator becomes smaller, overall, if I divide by a smaller number, won't the overall value end up being larger, and it's a greater that's opposite, greater force of attraction. So, you guys, we're going to relate that and help us to predict periodic trends, taking that into consideration. Oh, so that was the distance between, yeah. Okay, we're going to look at a periodic trend, guys. Atomic radius. And here's what we mean by atomic radius.
Try this. The dimensions of a jigsaw puzzle can be measured in meters. The dimensions of a single piece of the puzzle can be measured in centimeters.
Okay. But atoms are much smaller than that, you guys know.
That's 10 to the minus 12 meters, or 0.0000000000001 meters.
They're talking that we would measure atomic radius. You see the distance from the nucleus to the outermost electron in picometers, which is when they're saying 0.00. They're saying this is really, 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 really small. That's what they're saying, essentially. Okay, so we're talking to radius. So now you guys, we're going to make a periodic trend. So here's the question. From left to right in a period, what do you think happens to the atomic radius? Okay, so here's the periodic table. This is kind of difficult because I got to go back and forth, but that's just what we got to do, right? So we're saying let's choose elements in period 2. So we're going across. So the question is, as you go from left to right, do you think the atoms become bigger and bigger and bigger, or do you think the atoms become smaller and smaller and smaller as you go left to right on a period? Well, the reality is the atoms get smaller. You guys should actually draw, and it'll help you if you have a drawing. If you guys just put this, because you're going to be more inclined to remember it, just show atoms like this. Just kind of show them going smaller from left to right. Just do that. Just do some circles. Those are representing atoms. Okay? But you guys, I don't want you just to memorize that, because you're going to have a tendency to forget. I want you guys to understand, why is that? Why does the atomic radius decrease, goes down as you go left to right? One factor is, and I'd ask you guys, well, what do you notice happens if you guys were to look at the periodic table? What do you guys see changes? Hopefully you guys would look and you would see the atomic number gets bigger. So for example, like this is lithium on the left, it's +3, and then you got beryllium and so forth, and then you go all the way to fluorine, which is +9. What do you guys think about it? Think about what's keeping those electrons in orbit. Isn't it the negative electrons attraction for the positive nucleus? So when you guys think, if you have more protons in the nucleus, a greater positive charge, remember we were talking about showing that with magnets, isn't that going to have a greater force of attraction? So what's that going to do to electrons? The electrons that are orbiting, isn't it going to pull them closer into the nucleus? And that would explain why atomic radius decreases, because of an increase in the positive nuclear charge. And you would look on your periodic table and you guys would see that. Okay. But we also want to look at a trend from top to bottom. Okay, so I want you guys to, so then we would make a prediction. So as we go down, let's just say in a group, we choose a group, or you could call it a family. Let's go with, so in general, what do you guys think? Let's say we're going down the alkali metals, okay? As we go down, what would you guys predict? Do you predict that the atoms would get bigger and bigger and bigger? Or do you predict that the atoms would get smaller and smaller and smaller, the atomic radius? What do you guys think? They're going to actually get, show it guys, they're actually going to get bigger. And I know that would seem to defy you to say, Mr. Willison, but look, don't they have more and more protons? So wouldn't you use the same reasoning like we did here, right? 3 to 9. Wouldn't you use the same reasoning? So it does have an increase in the positive nuclear charge, but there's another factor that's greater than that. You think about when you go down, I'll remind you guys, when you go down, here, each period corresponds to a shell of electrons. So as you go down, you're having more and more shells of electrons. Here, I want to do an example here. 1 second here, guys. Okay. So, for example, lithium has 2 shells of electrons, but then look at sodium has 3 shells of electrons, and then look, potassium has 4 shells of electrons. And you guys think about it. If we're talking about the attraction of a positive nucleus, let's say for the outer electrons, right? The outer electrons are in the outer shell. When you guys agree these underlying shells of electrons screen out the attraction that the negative electron would have for the positive nucleus. It's kind of like this, guys. So I got, let's just say, right, we got, let's say this is the electron and this is the proton, right? There's an attraction. But now let's say there's a shell of electrons separating the outer electron for the positive nucleus. What effects that going to have on the force of attraction? Is there going to be more of a force of attraction or less of a force of attraction? Yeah, see, it's not going to hold. Yeah, it wouldn't hold. And then you guys think about, what if we had, right, more and more shells of electrons? What does that do to the force of attraction between a nucleus and the outer electron? It's even weaker. So if it's weaker, where would you guys expect the electrons to go? Would they be pulled in closer, or would they be moving out further from the nucleus? Would they be moving out further from the nucleus? And therefore that would explain why the atomic radius increases. So you guys put that, you guys, we usually use abbreviations. I'll just do an up arrow. You just get bigger. But you know the best thing to do is, you guys just draw it, because you're going to be more inclined to remember it if you draw it. And that's due to, we call it the screening effect. You got more and more shells. Look, these are all filled with electrons. They get in the way. They interfere with the attraction of the outer electron for the positive nucleus. And that's what this is saying. Underlying shells of electrons screen out some of the attraction an outer electron has for the positive nucleus. Ooh, So have you ever watched Nino eat barbecue in 3D? Oh, okay, that wasn't that funny. All right, one last periodic trend, guys. Stick with me. Guys, big concept. You guys need to know what this is. Write it down. Ionization energy, big word, so we tend to abbreviate IE. So whenever you guys hear IE, ionization energy, that's the amount of energy needed to remove the least tightly held electron from an isolated atom. Okay? That's the ionization energy. Think about, and when it says the least tightly held electron, what electrons would that be when you're talking about the one that's least tightly held? Wouldn't that be the outer electrons, right? The valence electrons? So, for example, look.
Ionization energy, that's the energy needed to remove an electron from a gas atom.
Okay? And you guys see, because that electron is attracted to the nucleus, and that's why it was otherwise orbiting that nucleus. So therefore, wouldn't it require energy to pull that electron away from the nucleus? And so that's what we call ionization energy. So the more tightly it's held, the more energy it requires, the higher the ionization energy. The least tightly held, therefore it's going to have a lower ionization energy. So this is kind of representing that, E for energy. This is a neutral atom. So if energy is applied to a neutral atom, what we can do is we can remove an electron, and then you guys remember, right? If a neutral atom loses an electron, it becomes positive. I know that seems kind of weird. It loses an electron, it becomes positive, but you got to remember, electrons are negatively charged. So if it has less electrons, it itself will become more positive. Okay. Neutral atom, and yes, so we had already stated that. Okay, you guys, we're going to finish with this last trend with ionization energy, trying to make a prediction. So when I do this, I'm hoping you guys pause the video, because I go right into the answer, because why wait if you can pause the video, and you guys try to predict. As you go left to right in a period, what do you guys think happens to the ionization energy? So we want to look at a periodic table again. Once again, we'll just choose a period. Let's go period 2. Let's say as we're going from lithium to fluorine. So we go to lithium and fluorine. What do you think happens to ionization energy? You're either thinking ionization energy increases. That means as you go left to right, it's harder and harder to pull off the outermost electron. Or does the ionization energy decrease? It becomes easier and easier to remove the outermost electron from these elements. So what do you guys think? The ionization energy increases. Hopefully you guys would put an up arrow. So the question is, why is it harder to remove an electron from fluorine than it would be from lithium? Guys, the key is, look at right here. Just think about, where's their outer electron? It's in the, by the way, these would all have 2 shells. So I'll just So they all have the same, right? They all have two shells of electrons. So why would it be harder, right, to remove the outermost electron from, let's say, fluorine than lithium? You guys should see there's actually two reasons. And you know what? I don't think we need the periodic table now, because we can just look at that and you should be able to state, why does the ionization energy increase? Due to, hopefully you guys realize that you guys are looking, notice, this has more protons. So wouldn't you guys agree, isn't fluorine holding on to it? Isn't there a stronger attraction between the negative electron and the positive, right, the 9 protons in the nucleus of fluorine than the attraction that this would have for the 3 protons in lithium? So that would explain why it's harder to remove electrons. Really, and you think about it, from the nonmetals, remember the right side of the nonmetals, it's harder to remove electrons. And then what's another reason you guys should be able to see? Guys, check it out. What do you guys notice is happening? The atoms are getting what? Smaller. So isn't this electron here closer to the nucleus here than this electron is to that? And we know the closer the opposite charges are together, the what? Remember with the magnets, the stronger the force of attraction. So both of those are reasons why ionization energy increases as you go left to right. So you know what? You guys can even put this on your diagram. You know, like I said, if you guys have ionization energy, just put, as you go this way, put increases. So what I'm saying, as you go left to right, it increases. Okay, you guys can imagine probably the last thing I'm going to ask you to predict is, well, what about if we go from, don't say right to left, because obviously, we know the answer to that. No, if it goes from top to bottom. Okay, so we can look at the periodic table, but we'll just look at here. Okay, so the question is that you go down. So this was like lithium, this was sodium, this is potassium. As you go down, do you think it's easier and easier to remove the outermost electron, or harder and harder to remove the outermost electron? The answer is, the ionization energy decreases. Basically, as you go down, it's easier and easier. It requires less and less energy to remove the outermost electron. Why might that be? I'm hoping you guys could look and you can see. Well, you can first notice, check, what's the first one I have? Okay. The first one is, you guys notice, we get more and more what? More and more shells. And what do you guys today with those shells? Remember, the shells interfere with the attraction. So the more shells, the less attraction. The less attraction between the nucleus and the outermost electron, the easier it is to remove. So you would say, you remember we call that the screening effect. More shells of electrons. And then, last one, you guys can notice it, the atoms are getting what? The atoms are getting bigger. So the outer electron and elements toward the bottom, the distance between the outer electron and the nucleus is much greater, and therefore the force of attraction is not very strong, and therefore it's easier to remove. So because of the increase in the atomic radius. All right, guys, I think that's enough. I think I blew your minds enough. See you next time. Bye.